Problem 11.7. Calculate the area of the ellipse x squared over a squared plus y squared over b squared equals 1. Okay, so we've done similar things before. We've dealt with this ellipse, right? This is a, this is minus a, this is b, this is minus b, right? Now the area of this, it's obvious that if we just deal with this quadrant and we can compute this area, the area of this ellipse is going to be 4 times this, right? Now this here, this y, we have done this before. This is b times the square root of 1 minus x squared over a squared. Check problem 11.6, right? We've done this before. Now the area of this is going to be, let's call it area of the ellipse, is 4 times this area, which is the integral between 0 and a of this function, right? B times the square root of 1 minus x squared over a squared dx. And as usual, we change the variable. X equals a times the sine of theta. And so we have, let's see, we have 4b, the integral between 0, when x is 0, sine is 0, and a is pi halves. And then we have the square root of this is the cosine, and then dx is a, the cosine of theta, d theta. So we have cosine squared and a that goes here, d theta, and we have done this integral before. This is pi halves, sorry, pi over 4, right? It's pi halves if it goes from minus pi over 2 up to pi over 2. Okay, you can do this. We've done this in 11.6, right? And this is 1 plus the cosine squared is 1 plus the cosine of 2 theta over 2. Then you have theta over 2 from 0 to pi over 2, which is pi over 4. And then the cosine, the integral of this is the sine of 2 theta over 4. And the sine of 2 theta at pi is 0 and at 0 is 0, so you get that, pi over 4. Okay, so you get 2, not 2, sorry, pi times b times a. Which again makes sense because if b and a are the same and are equal to the radius, okay, then this is pi times r squared, which is the area of the circle. Okay, so this is a generalization of the area of the circle. Okay, again, good. Now let's go for the next part. B, calculate the volume of the ellipsoid x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Okay, so here what we have is in 3 dimensions, right? Let's call this z, this is x, this is y, right? So this is the ellipse here, and then what we have is something that goes, so if we think about this in all of this crosses, right, this is an ellipse in all of them, right? So you get the composition of this thing. I don't know how to plot this, right? You get this kind of balloon if you want, right? 3-dimensional balloon. So what we want for the volume is we're going to integrate from here to here in z. So this is from minus c to c, and each point in the intersection, if you're going through here through the z-axis at some point z, what you're having is x squared over a squared plus y squared over b squared equals 1 minus z squared over c squared, right? So that's, at this point, this is the ellipse in which the in this point z squared is a constant, right, and c squared is a constant. So this is an ellipse in which the ratio, instead of being 1, is 1 minus z squared over c squared, right? So let's see, we can, how to say this, we can actually divide this, right? So we have this x squared divided by a squared times 1 minus z squared over c squared plus y squared over b squared times 1 minus z squared over c squared is 1. Okay, this is the equation for this ellipse when you're at the point z, in the z axis. Okay, this is z, you have this. Okay, so if z is minus c, right, you have the point 0. When z is c, you have 0 again, and when z is 0, right, you get the original ellipse, right? So this is a and minus a, b and minus b, but just 1 when z is 0, but it becomes smaller whenever you move away from z equals 0, right? So now from this, well, what we have to do is we have to integrate, and again, the volume of this ellipsoid is going to be twice the volume of the ellipsoid that starts at 0 and goes to c. You can see that, right? So this is 2, the integral from 0 to c, the area as a function of z of this ellipsoid. But the area here, using the area that we have just obtained, the area of the ellipsoid was pi times a times b, but now this a is a times the square root of this, right? And b is b times the square root of this. So what you have here is pi times a times b times 1 minus z squared over c squared, right? That's what you get. And now we just need to integrate this. Okay. And if you don't believe me, you can just compute the area of this ellipse using the same argument, but you get the same thing. So v, the volume, is twice the integral between 0 and 2 of pi ab, so then you have 2 pi ab go away, and so you have 1 minus z squared over c squared dz, and this is 2 pi ab times z minus z cubed over 3 z c cubed from c to 0. And so when let's see, when this is 0, everything is 0, and when this is c, you get 2 pi ab times c minus wait a minute, this is c cubed, c squared, sorry, not c cubed, c squared. So you have c cubed over c squared, c minus 1/3 of c is 2/3 of c, so you have 4/3 pi a b c. Okay. Okay. And now part C says check the result of problem 11.6.1 and 11.6.2. It's particular cases of the previous result. So remember, 11.6.1 was you get this ellipse, right? This one, and you rotate it around the x-axis, right? And the volume of this, let's call it ellipse x, is 4/3 of pi b squared a, and the other one was you had the same ellipse and you rotate it around the y-axis, and this volume is 4/3 of pi b a squared. Now, if you realize, if you rotate this ellipse around the x-axis, what you get is the same ellipsoid that we have just been saying, right? It's just that this ellipsoid is, instead of this minus c, right, and minus b here, this is minus b and this is b in the z-axis, right? And then this is a in the x-axis, right? So this is a special case of this general ellipsoid, but when c is equal to b, right? So if c equal to b, you get b squared. And you can see that the same thing happens if you rotate around the y-axis, is that here now c is equal to a. And that's how you get the volume of the two previous solids of revolution.